So, continuing from last day, we're looking at reducing dimensionality, but doing it in this funny way where we first increase the dimensionality into a nonlinear space and then decrease the dimensionality, looking for structure there. And the whole idea is that to not confine ourselves to just looking for things that lie near subspaces, near planes or hyperplanes, or any linear subspace, any linear manifold, which is a subspace that can be offset, so located anywhere in higher dimensional space. So we want things that are nonlinear manifolds. Can we try to capture that? And so the idea here is that, well, let's map that into a higher dimensional space that's got a whole bunch of nonlinear components in it, and then look at doing dimensionality reduction in that higher dimensional space using the inner product on that higher dimensional space. And as we noticed before, the relationship between the methods that we're using principal component analysis are based primarily on the inner products, looking at that Gram matrix. And so all we need to have in the higher dimensional space is the Gram matrix, which is the value of the inner product at any particular pair of points. So if we have that, we're in business. And that's called the kernel function. And last day we talked about some simple polynomial kernels here where we're looking at the scale sigma x transpose y raised to some power d, or a radial basis function or Gaussian function. Here looking at the Gaussian density and with scaling parameter sigma here. The thing to note, which I'll point out in a second here, is that this scale sigma here is a true scaling in terms of the scale of the data, and so it's dividing everything here, all the x's and y's themselves, as compared to here where the scaling is being multiplied. And similarly here with a hyperbolic tangent. So there are lots of different kernels to choose from. So that we've talked about, and I want to just start looking here because this particular data that we're going to look at, the Frey image data again with the functionality for kernel principal component analysis. It's just decomposing that Gram matrix on the higher dimensional space, that kernel matrix that's centered in rows and centered in columns, and taking the effectively principal components of that matrix. So it's just taking the eigen decomposition of that matrix. So the radial basis function here. So the note that I point out here is that I didn't mention last name is that this sigma in Kern Lab is actually sort of the 1 over 2 sigma squared. So it's not the same as our sigma. Okay? So let's have a look. So when we do that in R, we have this radial basis function with that sigma and these eigenvalues. When I look at this plot, you see that there's not a huge, the scree plot is not showing a rapidly dropping off, sort of indication that we're not going to get anything out of this particular choice. And when we looked at these last day, we saw that there was a lot of points that were piled up and just points separated by themselves. So I'm just going to change the sigma slightly. I've already pre-computed this, so it's not slightly, a few orders of magnitude difference, and pick off these eigenvalues, and hopefully that may produce a slightly different scree plot. Yeah. So now you can see with that transformation into that higher dimensional space, those sets of inner products, we may be able to reduce the dimensionality considerably without losing too much structure in the data. So, as I said last time, we'll look at 20 points. So I'm going to take reduce to be the first 20 points of this and do the scagnostics on that. Evaluate all of these and have a look at the data. So this kernel principal component analysis on the Frey image data. So let me just pick all of these, make them little circles. So that's our navigation graph. Down at the bottom, I'll make this relatively small. The inspector. And this is the pairs plot of the scagnostics and the corresponding scatter plot. So that's it on the first two principal components. So again, you can just have a check to see how that's preserving or not the going to selected, the nearness of those points in the 560 dimensions. So now we actually are seeing guys that could look kind of like in that same region. Scale to world and bring these back. And we could explore different parts here. So again, what are these guys? Let's just set these. What are these guys? So I don't know the answers here. I'm just looking at, thinking about this top half of the cloud. And there does seem to be some relationship here between the points. Okay. So in each of those things, at least in the first two principal components. Oops. Send them back. And to the world. All. So we could use the scagnostics again to see what might be interesting. And perhaps it's clumpy, non-convex things that might be interesting. That's the second and third principal component. And look for structure as we move around on this set of variables. And the interesting thing in my view is we've got quite a selection here of different pairings rather than just the first two. So beginning with V2, V3, and you'll see lots of other sort of characteristics suddenly appearing, which again are sort of interesting. I'll just pick out one of these, like this line here. Just curious, why is that appearing in some vaguely linear fashion? And scale to selected, and see what are we looking at. So a bunch of smiley faces here. Is there a transition moving from one to the other? I'm not so sure. So this is where things become a little bit of fun, looking for why are these particular rays appearing here in different locations. Okay, and I'm just going to look at these. Selected. And it's kind of hard to imagine how that transition's moving, whether it's the orientation of the head, certainly this pouting face that he's got. So they seem to be picking up these clusters. Any questions? So you can have more and more fun with this by going to these higher dimensions to see what structure there is in the space, perhaps identifying clusters. Um, and as I said before, reducing this down to 20 dimensions. Whoa. Wrong one. Click on that. Curious. So every structure I see, I want to look at the faces to see what they are, what the connections are between those. And again, maybe looking at, let's pick up where striated, skinny, stringy, striated. So the ones that are most showing lines. These may be some of the same ones that we've seen before. So again, you can see the lines showing up in some of these. Okay. So let's try another kernel. So a polynomial with a degree 10. Oh, I've already calculated. Oh, good. That's fine. Let's see what this looks like. Scree plot. Again, looks like there's an opportunity for substantial reduction in dimensionality. You know, 1, 2, 3, 4, 5, 6, 7, 8. So if we pick off first 20, maybe we're not so bad in capturing the variation that we seem to see in that data. The thing notice is that, as I've done here, you can have more than one transformation operational at the same time. We're linking them with the same linking group, and they may be showing up different patterns. So here, and now this graph is down here. This scatter plot matrix is to deal with these positions. And again, all circles. And so we might say, are there lines here? So these guys have outlying. Anybody have any interests? What we might look at? High striation. Wow. So here's that group with the highest values of the striation. And that doesn't look like that's showing up very much in the way of lines. Certainly it's all on V14. So even though the striation level is the highest, it doesn't look like there's much there. As we switch around, these guys are not connected. Doesn't look very striated. Oh, there's something. Okay. So not so much there. And you should see that should show up when I go to 0, 1. Yeah, look, there's hardly, those values are actually very low on the 0, 1 scale. So those are the lines showing the most lines in this data set, but there really aren't any lines there at all. So, you know, maybe the least convex guys. With this polynomial plot. So you see these different transformations are going to give you different results to investigate. So this is the least convex. Well, that was interesting. versus, let's see, these guys. Huh. Roughly happy and sad, those two groups that we just saw fly by. So all, and back to the world. So not a bad way for exploring this data. I must say that this data shows a lot of smooth transitions, because remember how it's made. It's the guy's making a movie of his face, and he's just making faces in front of the camera. So the frames are going to be very close to one another. So you should see kind of smooth transitions. If you did faces in the wild, you know, like if I just took your faces all there, maybe 5 shots of each of you, it won't be as smoothly changing, right? Because it'll be abrupt changes between how the face look. Probably pick up the guys that have glasses, tend to look alike. Guys that have beards tend to look alike in this high-dimensional space. Okay? And there are other data sets out there that you can look at. There's a nice data set of employees from Olivetti that you could look at. Question?
Yes. So if you grab a group like you just did, you find out like they have an interesting various, like interesting that you want to look at inside of Loon. Are you able to like isolate which values are unique with them?
Okay, so two things. I guess one is that say I do identify groups here, and so then I color them all, right? So I like that. I mean, we're cheating a bit because we actually have a face to look at. If this was music, right? So it's a big thing that I don't have anything to look at. It's a little harder to make the case. But say I go through this and I color them all different colors, depending on the group. So take the faces away, I guess. I might think about having identified these groups and giving them labels, right? That those are the groups I think are near each other in this higher dimensional space. Then I might look at pretending I have those labels in advance and saying, can I identify a method that will, from the original data, that will separate those groups? Maybe I'll get some interpretability there. No guarantee, right? But I think that's probably the way I would proceed. Okay. I mean, it's just cool because it's faces. We can actually see they happen to look alike when they're in the same neighborhood, which should give you some reassurance about the methodology being used for these kernel principal component analyses. And again, they're linked. So things that I see, you know, here, I wonder, that's clearly showing up a different group there. Where are these guys in this other representation? So this is a kernel PCA with a Gaussian kernel or radial basis function kernel. This is a PCA with a polynomial kernel. So if these guys seem to be agreeing, I'm a little bit more reassured even that perhaps this group is out there in this higher dimensional space. So restricting yourself to one method seems kind of unnecessary. Okay, other questions? All right. Okay, so what are we doing? Well, we're taking what we know about principal component analysis, which all works on that matrix, the Gram matrix of the inner products, and we're saying, let's move that to a transform data space, nonlinear transformation in a higher dimensional space, and then do our principal components again. How else might we proceed? Well, there are other relationships here with the Graham matrix. And that is thinking about the distance. So again, think about the Euclidean distance between any pair of points in let's say the original space. So I take the squared Euclidean distance, and you know that's just the inner product of the the squared length is the inner product of that difference with itself, which is just expanding that xi transpose xi, etc. Those are just a bunch of inner products. That's inner product of xi with itself, xi with xj, etc. So these are actually elements of the Graham matrix. So if I think about this if I had the matrix of squared distances, okay, call it D star, this equation tells me what each of the elements are. So the ij element of D star is going to be the ii element of the Graham matrix minus twice the ij element of the Graham matrix plus the jj value. In matrix terms, that's just saying if I think about G being the vector of I guess I need a G. Yeah, no, G is the vector of the diagonal elements. So G is the vector of G11, G22, G33, etc. I didn't write it on the slide, but that's what it is. That can be expressed in matrix form. So I've got a relationship between the squared distances and the elements of the Graham matrix. Okay? Everybody with me? All right, so if I have that to start with, and I pre and post multiply this by this centering, right? I minus 1 transpose, 1 inverse, 1 transpose, right? So I'm projecting onto the space that's orthogonal to the 1 vector. Pre and post multiply. Just a little bit of algebra here. Leave aside this right-hand component first and just distribute this matrix over the interior here. That's going to be that times 1G transpose minus twice that times G plus that times G1 transpose. And the beauty of that is that this is projecting onto the space orthogonal to the 1 vector. And the first vector I'm projecting onto that is the 1 vector. So that's going to be 0. Okay? I can make that 1 disappear. So this term here turns into that 0. Okay? Minus twice the rest. And then now I bring this thing in from the right-hand side. And I'm going to have minus twice this times G times the same matrix again, plus G1 transpose. Now I have this piece. Again, I'm projecting the 1 vector onto the space orthogonal to the 1 vector. So that too is 0. Okay? Any questions? Everybody see that? Just need to recognize that I minus 1 over n 1 1 transpose is projecting onto the space orthogonal to the 1 vector. Or just do the arithmetic. Just take the 1 across there and you'll see it'll all disappear. Okay? Up here? Yeah? Okay. So, what do we have? Well, we've got this equation is what we just derived. And then remind you that the gram matrix, we've centered the x's. So when I sum those x's, right, they sum to 0. So everything is already in that space that's orthogonal to the 1 vector. So when I multiply this by g, I'm just going to get g back. And the same the other way. So in fact, this ugly mess is just g. It's just the gram matrix. Okay? Remember, g is xx transpose? Okay? So I'll leave that for you. Work that out if you're having some difficulty with that. But it's by the way we constructed the gram matrix with, centering everything. So that means we've got this nice relationship that if you give me the squared distances, I can get the gram matrix. The matrix of inner products. Right? And if I have the matrix of inner products, I can get its eigendecomposition. And if I can get its eigendecomposition, I can take a subset of the eigenvectors. I can do principal component analysis. Okay? Everybody with me? So let's just, once more with feeling. Just think about what we've done here. So I've got the distances. If I have the distances between these objects, I and j, right, xi and xj, I've got the squared distances. However I arrived at them. I know that that's related to these gram components, which I can write in this particular way. And this is, it's not obvious why you would do that, except to make maybe these bits disappear. In the end, I've got this relationship here between the matrix of squared distances in the gram matrix, and this wonderfully simplifies to just minus twice the gram matrix, which means the gram matrix is minus 1/2 times this piece. And if I have the gram matrix, I could do an eigendecomposition of that, do a principal component analysis. Okay? Any questions? Okay, so that's the story. You can start with distances, you can get to the gram matrix, or square distances. That's a cool thing. Why is that cool? Well, it might be another way of thinking about dimensionality reduction. As I said, I didn't say how I came about those distances, but I have distances between things. So distances between images, distances between songs, distance between whatever. I've got measures of distance, however they come about. More generally, dissimilarities. They don't even have to necessarily be distances for us to try and force this. Then it becomes non-metric, but still works. So if I have these distances, if you think about, suppose data looked like this, Swiss roll. So this confectionery. So it's a sheet of paper just rolled up. And you say, if we think about the distances here, the Euclidean distances between these points are ignoring the fact that the points are on a manifold, a nonlinear manifold. This distance here between these 2 points, that Euclidean distance, doesn't seem like the right distance. if I were an ant on this manifold, I can't jump across this chasm. I'm going to walk around here to get there. So the real distance between these 2 points is following that manifold. So if you've got those distances, the distances between every point on the manifold by following the manifold, use those distances, I can get a Gram matrix and figure out, can I get now a Euclidean space that where points that were close to each other on the manifold are close to each other in the Euclidean space in our principal components. Points that were far from each other on the manifold are far from each other in the Euclidean space on the flat. So imagine we unroll this and turn it into a flat sheet. Okay, so that's our objective. Use those distances that are beforehand, find Euclidean space. Maybe that rather than 3-dimensional we see here, we only need a 2-dimensional space to preserve these relationships. And what we're doing is we're preserving local distances. Okay? Make sense? So, next thing is, well, what is local? Well, what we might do is have every point look at its near neighbors. You can imagine how you would do that in a couple of different ways. Maybe I look at all the points within some epsilon distance, Euclidean distance of me, right? Think about those. Or I might just say, give me my k nearest neighbors. Okay, so I find the nearest neighbors for some value of k, is a simple way to proceed. And then I draw a graph. Imagine each point is a node. And draw a graph where the edges are between any pair of nodes if one is amongst the k nearest neighbors of the other. Okay? Now I have a graph. And if k is small enough, I'm really looking at the nearest neighbors. I'm really looking at the local neighborhood, trying to preserve that. If k is too small, the graph may be disconnected. So I may want to have k be large enough so that graph is connected. All right? Good. So what, if I have that graph, how might you imagine measuring the distance between 2 points? When you think about the topography of the Earth, right? We have mountains and valleys and great expanses of water that you can't cross, but you have to drive from one place to another, say in Eurasia, or just in North America. So we're driving from one place to another here. And you have roads that are connecting them, right? Yes? Do a graph traversal. So close. So you find 2 points on the graph, and you do a graph traversal. Any graph traversal? Sorry? Oh, okay. Well, what are you trying to find in your search? Pretend you're looking at Google Maps. What would you do? Google Maps gives you 3 different routes, the shortest distance. So you want the shortest path, maybe, between any 2 points following the graph edges, and the distance be the sum of the distances of every hop. Okay? Does that make sense? Make sense, yeah? So we'll just do that sort of thing. And if we say, let's get the nearest neighbor graph for some value of k, and say, okay, now I need to find the distances between any two points, and I follow the nearest neighbor graph along the shortest path available to get that distance. And I'll need a shortest path algorithm. Okay? Then I use those distances, get the Graham matrix from them, look at the eigendecomposition. Maybe there's a smaller dimensional space that's now all Euclidean that I can place the points where those distances are very much like they were in the original. They're close to. So for example, in this particular instance here taken from a paper, if we're looking at these points, the Euclidean distance between them as opposed to traveling along the manifold, and here I produce the nearest neighbor graph by some definition of nearest neighbor. I follow that graph to get the distance. I get the Graham matrix from the distances. I take the first two principal components and I lay them out here. So now every point that's here appears in a plane. And what you see here is in fact the graph. So those are the edges that we had on the manifold. Now, the distance in the plane here, the Euclidean distance that we're using is this blue line, and it's kind of close to the distance of the red line following the graph. I mean, that's a little bit of fakery there, but you get the idea. Yeah.
So what happened to the second step? So the second graph?
Here?
Yeah.
So that's just used to calculate. So you imagine that this red curve here is is the shortest path along the nearest neighbor graph between those points. That's that same curve there in the plane.
So from A to B,
From here to here?
Yeah.
I see. This is an imaginary that we actually knew the manifold, and you can go anywhere on the manifold. So if it really was a sheet, I'd follow the shortest distance on the sheet. I don't really know what it looks like, so here's my approximation of what it looks like giving the nearest neighbor graph, which means in some cases I may be going around things. I may not be taking the shortest distance on the sheet because I don't know that, but I'm following something close to that. Okay? Other questions? Yeah?
Can you explain again how you go from B to C?
From B to C? Okay, so I have the nearest neighbor graph, which I construct in B for any 2 points, and those are just, you know, archetypical 2 points. What's the distance between them? It's not going to be this Euclidean distance. I have to follow the edges of the nearest neighbor graph. There are no edges here between these two, so I have to follow these edges. Okay? I follow those edges. That gives me a distance. So I've got that distance. I have it for every pair of points. If I've got the squared distances for every pair of points, I can get a Graham matrix, pretending those were Euclidean distances. Okay, so they're Euclidean distance in some high dimensional space, but they're Euclidean distances. And then I say, let's do the principal component analysis of that Graham matrix. That will give me positions in the Euclidean space. So not this space, but in another space, the principal component space. And I just plot those positions. And all we're showing here is that this Euclidean distance, which is the straight line connecting them in the plane, and the distance following the neighbor, following the graph, the shortest path. They look about the same. Does that make sense? So that's all back to this stuff, right? The fact that I can start with a square distance matrix here and get a Graham matrix and do principal component analysis. So I can embed this in a lower dimensional space. It's not the same space, right? Because I'm not using the Euclidean distances here. I'm using the distances along the manifold. It's just I have to find a definition of what manifold is. And so that's going to be this one based on a nearest neighbor. Okay. Everybody got that? Okay. So here it is. So for every point, you determine a neighborhood of the nearby points. A variety of ways that you might think about doing that. I said k nearest neighbors, or everybody within some distance from that point, a fixed distance. Create the graph with the points as the nodes and an edge between each point if they're in the neighborhood of that point. And then we follow the, for any points I and j in the graph, we define this distance, delta ij, to be the distance along the shortest path between those 2 points. I've got the square distances, delta star. I get the gram matrix. I take the eigendecomposition to get the new point configuration. So these new feature vectors. This particular method is called ISOMAP. Okay? And the idea is to try and follow a lower dimensional manifold as defined by some nearest neighbor graph. But intuitively, it's kind of straightforward if you know that you can connect distances to the gram matrix. Okay? Does that make sense to everybody? Alrighty. So there is a package called dimred, which you can do ISOMAP and a bunch of other things. There's also another package called vegan that also contains ISOMAP. And we'll just do this here. Have a look at this. We have those. So I'm going to use 12 nearest neighbors, 20 dimensions, the same as we had before, and then this embed function telling you use ISOMAP with what I've just described for you, and nearest neighbors and the target dimensions for the embedding. Okay, that will take a little while. And what it's going to return is a data structure. Okay, it's done. It returns a data structure that is an object. In R, there are a few object models in the sense of object-oriented programming. This is the so-called S4 one. And so it has, instead of the $, it's got slot names. And so if you look at the slot names of that structure, it has a bunch of information, data, the new data, and also the original data, and how it was constructed, and some parameters used to construct it. So again, we're at the whims of whoever constructed this program, this package. So I'll just notice that there's a funny thing going on here, that the slot data itself is a rich data structure, and the data we actually want is on the slot data of data. Okay, so that's why you see at data twice. And I'll do the scagnostics on that. And the navigation graph. And put the faces on. So we have another method here that gives us some information, and it's definitely trying, rather than doing this map into a higher dimensional space and finding things, it's trying to use the distances on the manifold. Okay. So again, it's linked to the other displays. So I have the colors that I had before in that group that I looked at there. And you can see, you know, definitely two different groups here. Probably too many points here. And it looks like it's pretty much happy guys. And I've lost them. I'll find it up here. That's the beauty of this thing. And unhappy guys. Okay, so between those two things. So another method. And in the past, I don't know, 15 or more years, there's been a lot of research on this so-called manifold learning. Okay, just looking at trying to find lower dimensional structure in high dimensional space. And again, I caution you that the Frey data are very nice. They're almost like the Swiss roll in that because it's selections from a movie, you're going to see some sort of smooth. It's not surprising that they should be near some manifold of some dimensionality. So again, looking at clumpy guys. Let's see if we can get more of them. You're not necessarily always picking off the first two principal components. They're the first two, first and third, second and third, third and 12th, third and 20th. Okay? I need to get that guy off there so I can select him. All right, so seeing this structure and the kind of groups that might be there, you've got that nice separation. So these are the ones that are most showing clusters. Kind of density-based clusters. And that stops, I'll get this to, there we go. Okay. And we can play with any of that. Let's get that back to something interesting. See, no hands. I don't know. Looks like it's stacked it pretty much everything up. So where does this appear in the other group? You see, so it's definitely picking up a different kind of structure than the other dimensionality reduction method is. Okay. So, any questions on that? So we've used principal component analysis. So if you understand principal component analysis, right, we've got two obvious tricks to make that more general. Since it only depends on the inner products, move that up to a higher dimensional space, kernel principal component analysis. Lots of choices for what those inner products might be. Do dimensionality reduction in that space. Alternatively, look at the distances. If you have the distance between those, we can also relate those to the inner products, get the Graham matrix, and go ahead. Question?
How do you know to choose k-neighbors to be
Good question. So that one of the problems we have here with any of these methods are the choices of the various parameters. So for me, I would be choosing them to at least get me a connected graph, right? And then have it small. If I made it 40, 50, 60, if that was a Swiss roll, I may be crossing the boundary, so I'm afraid of making it too high. And unlike other things where we don't have a clear objective function, we can't really cross-validate this for all of the values of the, like you do in prediction or in a classification problem. So it is pretty much fooling around to see what you could see. It's an exploratory method.
So it's more like a trial and error.
Correct. Unless you have some objective function that describes what's interesting, and then of course I can find you the one that gets you the best value of that. But without that in hand, I'm guided by, I know I want, the smaller k is, the more local I'm using things, right? But I may have a disconnected graph. The larger it is, I may cross these boundaries. So suddenly it's as if I've got a road from New York to London, England, right? So you have to be, okay. Okay, one more lecture. So what I'm going to do is next time I'm going to give you one more dimensionality reduction, just for the heck of it, because it's similar to this one, and produces weird structures. And then I think Friday I'll do a review. Tomorrow I'll hand out the assignments, by the way, and we'll take it up. And Friday I'll do a review. Monday I'll take up the last assignment. Okay? Sound fair? If you haven't yet, and I assume everybody here has, please do the evaluate. Yes? Walk you through what you did? Yeah, I'll go through about 3 billion slides in 50 minutes. Yep, I can try that. I can do it on the blackboard or something, try to, with access to the slides, but yeah.